Welcome everyone. You're joining us for Quantum Efficiency Measurements, Fundamentals for Solar Cell Research, Part 1. This webinar is presented by MKS Newport and hosted by Photonics Media. Today you're going to hear from Ken Corelli and Dave Sobranis from MKS Newport. Their colleague Todd McFarland will be joining for the Q&A session at the end of this presentation. Ken is a product marketing specialist for Newport. Dave is an application engineer and leads the product specialization and customization program, and Todd is a lead development engineer at the company. In this session, they are going to share the fundamental measurements for a quantum efficiency system and how they apply to research and design of a solar cell. You can ask questions or leave comments in the chat box at any time. If you have any technical issues during the event, please log out and back in to rejoin. You will be able to access a recording of this online after the webinar, and you will receive a link to that recording by email. So with nothing further from me, I'd like to first welcome Ken Corelli. Welcome.
Yep, thanks, Joanna. Okay, thank you everyone for joining us today for our quantum efficiency measurements, the fundamentals of solar cell research, the part 1 of a 2-part webinar series. As Joanna has presented, we'll have myself, Ken Corelli, and Dave Sobranis going over the contents of the slides, and Todd McFarland will join us as well during the open Q&A session. To give you an idea of the agenda or topics we will cover in today's webinar, we're going to go an overview over the solar cell and photovoltaics energy market, why this is important and what's driving that demand. We're going to do some review of solar cell generations and their usage within these applications, as well as go over some of those design efficiency factors that need to be considered during the solar cell development. We're going to go over the quantum efficiency fundamentals, such as IQE versus EQE, and some of the equipment requirements, and touch on what you need to be aware of to set your lab up for success. And at the very end, we're going to focus on our MKS Newport products and service solutions to help guide you towards this process. So first, we want to go over the solar energy demand projection. And this is basically looking at a snapshot of consumption of energy in watts and compared to 2019, compared to how it was forecasted by Bloomberg to 2050. So this chart here is a nice data point to show in 2019 with the different types of energies listed at the bottom, where coal and gas made up about 50% of the sourcing for the demand. And you could see the clean energies such as hydro, wind, and highlighted under green solar make up a significant but less portion of that sourcing of energy. As you see, as we develop as a nation, as a country, as a global situation, we're going to increase demand of these energy resources. Industrial nations will come up and have more consumption. So not only will the demand go up significantly in that time frame, but also of interest is the clean energy portion will then dominate compared to the traditional coal and gas and oil type of energy sources. So you see 2019, it was 11% of the generation for solar energy. It's projected to be the most dominant energy source in the future. A lot of this comes from investments at the corporate level, at the government level of this clean energy technology to take advantage of our global consumption needs and demand increases. So what does this mean from a commercial perspective? So we look at the global photovoltaics forecast. This is all sources of PV type energies, looking at a snapshot of 2022, where it was and where it's projected to be at the end of the decade at 2030. And majority of this comes from solar panels, but this includes all uses of PV type energies. So this is consumer electronics, any types of end user products, as well as the traditional solar panels, which do make up a vast majority. You can see from this data point that it's going to double, over double by the end of the decade. And majority of this does come from PV panels. And another data point here, what this shows is a compound annual growth rate, also known as a CAGR, of 9.7%. And anytime you reach close or at double digits for that CAGR, it's of high interest from a commercial perspective and an investment perspective. So The initiatives are moving forward, the demand is going up, and there's a large market focus on this. Before we go more into the markets, I want to look at some of the basics of solar cells, and we kind of define these as 3 generations of solar cells. This is not just material types, but also the technology that interfaces with those solar cell type technologies. And this is a classical way to divide these interests and products into categories. First generation is mainly silicon, which is a composition of single crystal or monocrystalline silicon cells, or polycrystalline or multicrystalline cells. This has been around for many decades. It's considered an efficient type of technology, but as a comparison, relatively expensive. In terms of how it's manufactured and the cost of materials all go into how it's considered expensive. And again, the goal is to get as much energy out of a material with the dollars in versus what you can produce with energy out. These are rigid structures. Again, crystalline is in the name. They're reliable and sturdy, and they're ideal for static flat panel usage, as you see pictured on the left. The second generation, the amorphous silicon and other types of thin film type technologies, cadmium telluride and copper indium gallium selenide, is considered second generation. These are less efficient by comparison in terms of square area of material, but they are less expensive to produce. The thin film type technologies do produce and leverage that in terms of cost of production. These could be used for flat panels as well, but their flexible design also allows for novel use applications compared to the more rigid structured crystalline of the first generation. And then we get to the third generation, where a lot of focus is placed, where it includes different types of cell structures as well as technologies that those structures are employed. These include multi-junction tandem cells, organic photovoltaics, perovskites, concentrated cells, and other types of technologies. These have the goal of being efficient and potentially inexpensive once we develop more into manufacturing these and harnessing this type of energy technology. But at the current moment, it does have lifetime and manufacturability concerns. So it would be the best of both worlds as we develop this type of third generation cell for PV applications. But what does this look like in terms of implementation commercially in the most commonly used for the PV market, which is the PV panel sales? So here's a graph looking at some historical and future production of PV panel sales. From here, you can see in the green, this is the traditional silicon crystal cells making up a majority of that usage for PV panel usage, as well as thin film still having a significant share for this PV panel production. As you see where we are today, 2022, 2023, it's about 10% of the thin film or second generation usage for this type of application, with the majority going towards the first generation crystalline silicon cells. As we move forward, market, as we saw earlier, will continue to grow, continue to invest, and we still expect the usage of thin films to stay about the same market share, but overall will be focused on that crystalline silicon type technology. So that's for the commercial applications for industrial use, but there's a lot of testing and data and testing and driving the innovation at the research level, where most of you on the call are focused on. So this is a chart. Many of you should be aware. If not, it's at the NREL website. This is data collected from their interactive cell efficiencies, which is the goal to invest and develop new technologies that reach new certifying records. I've selected 3 within their interactive chart just for simplicity, showing base silicon first generation cells, cadmium telluride representing the second generation cells, and perovskites as the third generation. There are obviously many factors that have combinations of technologies, tandem cell technologies, multi-junction technologies, but these 3 have been selected for simplicity. As you can see, historically, silicon is making incremental gains overall, with this last recorded at 6.1% efficiency. Cadmium telluride of the second generation has been, again, less efficient, but still making incremental growth to where it is today at 22.4% efficiency. But of great interest is perovskites, which in such a short time frame about a fifth of the time frame that this data goes back to, has already matched the level of silicon efficiency at 26.1%. So again, monocrystalline silicon is still the widely used commercial application, as we saw in the previous slide, but perovskite is a high growth focus for research. And again, that equal efficiency is of great interest for developing higher efficiency, lower cost, higher energy output panels and other photovoltaic devices. Okay, that's it for kind of the market covering. Now we're going to go have a audience polling question, which Joanna, you can introduce the question for the audience to get their feedback on.
All right, so I'm going to launch this poll now. The poll question is, what type of cell technology are you most interested in or are currently developing? So I'll give you some time to start answering those questions. Get some responses in. Thank you, everybody. All right, I'll give us a few more seconds if you haven't voted yet. All right, and then I'm going to close the question now. And here are the results. You can see the last option overwhelmingly won. All right, so I'll hide that now. And I'll hand it back over now to Dave Sobranis.
Thanks, Joanna. So I will apologize to the researchers and PhDs, but we're going to start with the very, very basics here. So what wavelengths of light are we talking about for the solar cell? Mostly the visible wavelength, as you can see in the spectrum here. However, we do go down into the UV and slightly into the near IR, as we will see in the future slides. The energies in these different extensions, let's say, of the spectrum are less, but as these emerging technologies come in or multi-junction cells come in, we can start to take advantage of some of the areas that are traditionally harder to convert into electrical current. So you can see where we are in terms of the spectrum from X-rays, UV, IR, microwave. And this is again, the typical area that we're going to be of interest, which is also where our instrumentation and let's say detectors and such will operate within the spectrum. And if we go to the next slide. So again, the rainbow there is just showing the visible spectrum of light that you would see on Earth. And this curve, which I'm sure everybody knows and has seen before, the black line is representing what looks like a 5800 degrees C black body spectrum from the sun. And you can also see that the light that is not into our atmosphere yet, let's say in outer space, is represented by the yellow portion of this graph. So it does follow that curve of a black body very closely. And then as the light is coming through to Earth, there's a lot of absorption bands that happen as that light enters into our atmosphere and then reaching the Earth's crust. So there are different air mass, let's say, filters that can be used. The graph here is showing the air mass of 1.5. So basically, that's going to be the ratio of if it was perfectly coming down to Earth at a 90-degree angle, and the 1.5 represents about a 48-degree angle coming into Earth. So there's more losses. And so the red portion of this graph is showing what you would get at a, let's say, AM 1.5, and that would be a sort of a typical number that's used for researchers that are trying to, let's say, come up with an average of what the energy is at Earth. We can go to the next slide there, Ken. So one of the things that we have found, and we use a lot of the xenon arc lamps, is that the spectra of the xenon arc lamp is very closely matched to that solar spectrum. The xenon lamps are really a great light source because they have a very good, excellent match to the spectral response. The power delivery is very good, and the cost is also very good. They also have a good durability, so they last quite a long time in your research applications. LEDs are starting to come online. The LEDs tend to fall off as you get closer to the UV spectrum. You can see in this graph here that it drops off pretty significantly when you get to about 400 nanometers. You can also see that on the near infrared side of it as well, they tend to fall off in that area as well. So they are getting better. They are tunable. They are a nice way to provide energy that you can use in different spectrums, maybe not all the way into the UV or into the near IR, but in the visible spectrum, they do fairly well. I still say that the xenon lamp is probably the go-to source for all of your applications where you're doing your testings on solar cells. As Ken had mentioned earlier, the overwhelming majority of cells that are out there right now are the silicon module type of construction. This one is just a typical example of how a cell might be put together. I realized from the poll questions that people are very much interested in a lot of the future technologies, but this is what's, I would say, probably 90% or more of what's really going on in the production of modules at this point in time. And you can see that this is, the construction of this will have a glass top surface. There'll be some kind of a glue and encapsulant, which is very important. That glue needs to be environmentally durable. It also needs to be an index match well to the glass, because as you as the light is entering your module, at any point if you have any kind of index mismatch, you then have a reflection, and then that's energy that you're not able to capture. This progresses down into the bus bar construction, the actual silicon components with more bus bars on the backside, another encapsulant, and then finally a back sheet material. So this would represent, I would consider this a standard production of a module. So let's talk about the quantum efficiencies. And so what is the quantum efficiency? So the quantum efficiency is really, it's the ratio of the number of electrons that are produced from a solar cell compared to the number of photons that are shining onto that cell. So for an EQE, which is the external quantum efficiency, what you're really concerned with is the energy coming into your cell and the amount of electrons that are being produced from that cell. The cell, as I mentioned earlier in the prior construction slide, there's going to be some losses of that light coming into your cell. So you're going to lose some from a reflection. You'll lose some through the absorption of the glass top layer, and also maybe absorption through the adhesive systems. But you're not measuring that. So you're measuring the total amount of light coming in and the number of electrons being produced. So in this very, very simple example, we would have 6 electrons produced with the 10 photons coming in. So the EQE in this, again, very simplistic cartoon here shows about a 60% efficiency. And typically when we get into the IQE, the EQE will always be a lower measurement than what the IQE shows. And the IQE, which we'll talk to on the next slide, and I guess we can go ahead and go to the next slide, Ken. So the IQE is really getting down to how is the actual cell performing. It's trying to figure out what are the losses or what is the efficiency of the cell, and to try to then, let's say, remove some of the other aspects like the glass losses and reflections to really understand how your chemistry is working. So the IQE then is the same, it's the ratio of the number of electrons produced by your solar cell. And but you're also very concerned about how much of those photons are being absorbed by the actual cell. So what you need to be able to do in that regard is to start accounting for the losses of the light coming to your cell. So those losses can be in reflection, as this simple example shows. We have the 10 photons coming into your cell. We have 2 of the photons being reflected, and those were measured. And so once those are known and measured, we're still producing the same 6 electrons on the output side, but if you subtract the 2 measured reflected photons, you have 6 electrons over 8 photons. So your efficiency then in this very simplistic case is 75%. So it's a very important, when you get into the IQE side of your analysis, that you have accurate equipment that is looking and measuring the different ways in which the photons coming into your cell are lost, or lost through, let's say, absorption in the glass, if there's a glass component on top of your cell. And then there are some cells, which I'm sure some of you are working on, that are translucent. So there's even a component where you might have a transmitted piece of energy going through the actual cell, which we can look at in this next slide. So this would be, let's say, a cross section of a typical cell. And you can see that the incident light coming in is going to first strike the upper glass surface. This would be for a constructed module. That top surface reflection, which we have here as R1, is going to be a certain percentage depending on whether it's AR coded or not. There's also a component of diffuse reflection represented by the small little blue lines and vectors coming off of that. If there is an air gap between the glass and your cell, and in this case we show it's reflective coating, there's still a loss there, and there will be a secondary reflection, which we show as R2. Additional to this, you'll find that a lot of the constructed modules today are using what's called low iron glass. The reason that that is the case is that low iron glass has a less absorptive transmitted component to it, which means that more of the energy coming into that glass will transmit through the glass and not be absorbed. So that is another component to be aware of. And then I mentioned previously that there are some cells that are being developed that are translucent. So you'll have a component of your light coming through the actual cell all the way through, which you would need to account for. So these are all of the things that you would need to consider when you're setting up testing on your particular cell. If any of these are areas that you are concerned with, then you would want to set up your detectors and instrumentation to capture this, so that you could then get very accurate information in regard to, and specifically in the IQE measurements. So this is a graph that many of you researchers know and see all the time. This is the graph that would show either an EQE or an IQE response versus wavelength. If you had a perfect cell that was magical and could actually produce 100% efficiency at every single wavelength, you would get the rectangular shape shown in the sort of the brown outline. What you're able to do, though, is with different types of instruments, you can then shine a monochromatic light. So basically it's one color of light, one wavelength, and you can change that wavelength. And as you scan that wavelength across, you are able to then monitor how much current your cell is producing, and thereby effectively create a EQE or an IQE curve. And it'll have this distinctive sort of upside down U shape. And obviously the closer you can get to that brown ideal, output would be an overall efficiency of your cell being really fantastic if you could get as close as you could to that brown outline. So there are many different ways to actually produce the light that you need for the monochromatic light coming into your cell. And in this case here, these are just very well-known technologies. You could use prisms, gratings, LED tunable light sources, You can even use bandpass filters. Each of those bandpass filters can be fairly narrow, so you can use it as sort of a point of light of light energy, and then you can build out your EQE graph using these multiple different bandpass filters. We use a lot of the grading technology in our products, so we can use a broadband light source like a xenon light source, for example, and break that light up into the colors of the rainbow. And then we can, by moving that grading, we can then select different wavelengths of light and thereby create the different light energies that you need to go through and scan the entire cell through the wavelengths of interest. So everything I've talked about is really related to a single cell style of solar cell, but what about multi-junction cells? I also noticed in the polling questions, there's a lot of people working on multi-junction cells. So can this be measured in the same way? Yes and no. Yes, you can do this as long as the cell is actually all the layers within the cell are active. So most of the multi-junction cells, as shown in this first picture, are connected in a series electrical format, which means that if any one of those layers in the multi-junction cell are off or not getting energy to activate it, the entire cell's off. So if you were trying to find out, for example, your layer 1, and you were trying to find out what was the EQE efficiency of that particular layer, you would not get a result in this case because the Y2, lambda 2 is not lit up, it's not active, and therefore that cell is off. So what you need to be able to do is to be able to shine a light bias onto a cell like this. And that light bias then can be used where there are different filters that you can put into, for example, the picture we have here is one of our MKS solutions. You can put different filters in to then have different wavelengths of light shining on your multi-junction cell. The idea is that you want the multi-junction cell to be fully operational so that you're actually getting a current output. And what you would be able to do then is you could then shine monochromatic light onto that cell, and you can actually set it up so that it's a chop signal, and you would be able to figure out then what was the change in your current using that chop signal coming into your cell, and then you would then be able to graph the EQE/IQE of each of those layers, depending on the wavelengths that you are shining onto that cell. And in fact, this next picture, the next slide will show you what that might look like. So this would be a typical multi-junction cell where the light bias is shining on that cell. We have a separate test light coming in. The test light can be chopped at different frequencies so that you would be able to then put together what would be 3 different EQE curves, and you would be able to then analyze how did each of these layers respond to the wavelengths of light and what is their efficiencies. If you were to combine those all together, that would give you the overall EQE. But from a scientist perspective, the people on this call, you're probably very much interested in a particular layer and maybe optimizing that layer and changing how that layer may be coded, put down, and created to either improve its efficiency or maybe even expand the wavelengths in which it's operating in to balance that cell. So that is a good way to go for a multi-junction cell, is to use a light bias system. And I think that, Joanna, you will be doing this next polling question.
Yep. All right, so I'm going to launch this next poll. The question is, what is the PV device area that you are most interested in or are currently developing? So give us some time to answer that. Thank you, everybody. I'll give us a few more seconds if anybody hasn't selected their option yet. All right, and then I'm going to close it, and here are the results. All right, and now I'm going to hand the call back over to Ken.
All right, thanks, Joanna. Thanks, Dave. So we began to scratch the surface in terms of the factors to design your cell around, the testing equipment you need to generate the light, to bias the light, to filter or chop the light. And I want to take a moment here as we end or get to the end of the presentation to talk more about MKS Newport and how we can support and be your partner in this type of application. One of the sayings or mottos of MKS is we surround the workpiece. This workpiece can be any device, any electronic component, semiconductor device, and in this case, it's the photovoltaic cell. So we have methods of way of generating light, as we've seen early in the presentation, whether it be a broad spectrum solar similar light, whether it's a tunable light source, getting monochromatic light tuned to your sample, so you can shine that and move that to your sample. We have ways of detecting and measuring all the sources of light, whether it be reflected or diffuse, and through different methods of calibrated detectors and power meters. We have other methods of measuring the efficiency through PVIV efficiency tools, other optomechanics, such as choppers, filter wheels, that can best automate and get your tested sample to the right type of test condition you need, as well as full integrating sphere and quantum efficiency measurement solutions, making this a turnkey system so you have this set up for success in your lab. Also, I want to take a moment to mention our photovoltaic testing lab services. This is an MKS Newport PV lab. This is available to test and certify your prototype PV devices. So while there's equipment out there to test in-house the performance, we also have this option to have your cell sent to us and perform the full gamut of tests with our equipment for these efficiency records. As we saw earlier with the NREL chart, all those record efficiencies are tested in a lab such as ours, so those can be recorded and published for your needs as a certified record as a governing body. Our MKS photovoltaic lab is located in North Logan, Utah. It is certified to the ISO IEC 17025 standards, and it is accredited by the A2LA. So for your samples, you can get testing performed and certification performed on individual components, whichever is the highest performance of your sample sent in, and use that for your own records. We do the full cell electrical performance test under the simulated sunlight conditions according to the ASTM standard E948. And we also perform the cell spectral responsivity to the ASTM standard E1021. All of these measurements are performed under standard reporting conditions. We have temperature control cell to the cell. We have the full 1 sun irradiance at the spectral irradiance of air mass 1.5 G, all according to the IEC standards. And as mentioned, all the equipment and the results are traceable to NIST and NREL for your records. At the bottom left, you'll see the total measurements that are included with your service here at our North Logan facility, including your fill factor, spectral correction, your voltage, max power, short circuit, open circuit. All of those requirements are included on a certificate for your needs. And as we mentioned, we just scratched the surface of the equipment needs. So we focused on the basics and the fundamentals of quantum efficiency. Our next webinar, which is scheduled for February 21st, goes deeper into the test methods. We have kind of a sneak preview here of a diagram, what we will go over in that webinar, showing the different individual components that you can select to set up this measurement, as well as the options we have within our MKS Newport portfolio. We'll go over multiple different ways of testing this through EQE and IQE test methods. So there's more than one way to test the efficiency of your cell, depending on what's most important for your research. So we'll go over the detailed equipment overview and individual components that you can select from our catalog. We also will go over specific device under test interfacing, ways to interface with your cell, make contacts to your cell probe points, as well as controlling and maintaining your sample, such as temperature control. Also, we'll go over, although it's not a quantum efficiency per se test, the PV-IV curve testing, where you'll use a broad spectrum full irradiation of your sample, can also perform additional ways of testing the total output and efficiency of your device. So look forward to that webinar in the early 2024 timeframe. Okay, so that concludes our part 1 of the webinar series. So now we will go open up to a Q&A session, which again will be joined by Dave and myself, as well as Todd McFarland, to handle the questions from the audience.
Thank you so much. Yes, we have time for a few questions before we close. Everyone, if you have not already, please go ahead and type those questions and comments into that webinar chat box. All right, so let's see. The first question I have here is, what equipment would I need to perform an EQE or IQE test?
Good question, and maybe we can. I don't know if we can refer to Dave's slide 18 or something like that. I mean, one thing is you need a monochromatic light source. And Dave had multiple methods of getting that monochromatic light. And then you'll need some sort of power meter or spectrophotometer to know how much of that, how much light is being output, so that you can get the incident photons on your device. And then you will need an ammeter to measure the current coming off of that, so that you can calculate the number of electrons from your test device. And then additionally, if you're trying to do IQE, you will want another meter to, yeah, this is actually an excellent slide. You need another meter to capture, you'll need a method of capturing and also measuring any reflected light off of the test cell, so that you can determine how many photons were reflected from it. Hopefully that answers the question.
Great, thank you so much. All right, let's see. This next person asked, what is the difference between a multi-junction and a tandem cell?
Interesting. I see these terms used in quite interchangeably. The best of my understanding, and just reading through papers, is that multi-junction, typically junctions in this case refer to the PN junction. So multi-junctions mean that there's at least 2 or more PN junctions. When they refer to a multi-junction device, typically I've seen it referring to devices with PN junctions of different chemistry. And then when referring to tandem, I've seen that cover both multi-junctions with multiple PN junctions with different chemistries, but also encompassing PN junctions of the same type, such as like bifacial solar cells, where there's a silicon cell on the front side and a silicon cell on the back side. And I don't often see, or even with silicon with different doping in the same one as a tandem cell. But I don't often see those things referred to as multi-junction. So in summary, tandem encompasses both the multi-junction and these ones with the same chemistry, but multi-junction usually refers to PN junctions of different chemistries.
Great, thank you. Let's see. This next person asked, are there any long life perovskites already available, and are any that are reel-to-reel printable?
I occasionally see papers of long life perovskites, and it just depends on what is considered long life. Sometimes people will consider hours long life, and some might concern weeks. I don't have a great answer for this, and I also don't know of any reel-to-reel manufacturing of that.
All right, thank you. Let's see. This next one is, are efficiencies based at temperatures of 20 degrees Celsius?
I think if you saw from our slide, most of our reporting does measurements at 25 degrees C Celsius. There's at least in the silicon world, there's lots of ways to adjust for temperature differences to calculate what efficiencies you'd get at the other temperatures. But most of all of the measurements that we do and we typically record is at 25 degrees C. So, and that's usually what's published with the NREL studies that we see as well.
Wonderful, thank you. All right, this next person asked, is there a minimal solar cell size that an EQE device can measure?
Also a good question. In our EQE solutions, we have a 1 millimeter beam size. It's pretty much square, and that's the minimal size that if you were to get a Newport IQE EQE system, you could measure down to without some other customizations. Other than that, we have shown customers how to use an aperture to get even smaller than that. The important thing is that you use that aperture when you measure the incident photons, as well as when you put the device down to get to smaller sizes. And so I think in reality, the smallest size is going to be limited by dispersion, the wavelength of light that you have. So I don't think that there is a limit that you can measure, but it becomes more difficult if it's below 1 millimeter in size.
Great, thank you so much. Let's see. This next person asked, do you need light bias for a tandem cell with a 4-terminal connection?
I believe when they're referring to 4 terminals, they're referring to 2 terminals for each junction there rather than a Kelvin connection. And the answer there is no, because those cells, those PN junctions will operate essentially independent of each other. You won't need the light bias to light up one. Dave's slide showed those when they're in series, they will limit the current from the other, but you can but when you have separate terminals for each junction, you can run your monochromatic light across one, measuring those 2 measuring that junction, and then go and measure the other junction independently without any additional light bias.
Great, thank you so much. Let's see. So this next question is, how do efficiencies decrease at, say, 100 Celsius or 200 Celsius? Are there ways to keep efficiencies from declining?
I'm going to pause there because I'm not a chemist. Ken, Dave, do you have anything?
Yeah, I guess that would kind of go back to the researcher and actually testing that. We do have temperature controlled chucks that we put cells on so that we can control those temperatures. I would assume that you would do that and work your way up in temperature and see how the efficiencies are changing as you change temperature. We are not experts in the cell construction, but we would certainly be able to help you come up with equipment or detection scenarios on ways in which to measure that, and then probably you would be developing that as a unique response to your type of cell.
And the only thing that I can think of to add is that, I mean, increasing the passive cooling, adding more surface area or things like that are not necessarily ways that you can increase the efficiency at the higher temperatures, but it are ways to cool the device more efficiently, so that it can maintain a lower temperature and better efficiencies.
Great. Thank you both. Let's see. So this next question is, can a quartz tungsten halogen light source be used as the broadband light source for testing EQE and IQE efficiencies?
Yeah, there's some, I think Dave mostly referred to the xenon lamps in this presentation, but there's, but a QTH lamp can be used as the broadband light source. Of course, you still need a filter, a light filtering element. There's some benefits to quartz tungsten halogen in that it's most closely matches a black body spectrum, and therefore there aren't a lot of variations of light intensity over spectrum, which allows you to have lower measurement uncertainty over parts of the spectrum. But the drawback is that they don't burn as hot as the sun, and they've got a lot less UV component. So if you're working in CAD Telluride or perovskites or things like that, there's not as much light to measure in the UV portion, and so the measurement uncertainties go up when you're looking at the QE between 280 and 320, 360 nanometer.
Great, thank you so much. All right. So this next person asked, can we send in sample cells to MKS PV laboratory to get either an EQE or an IQE graph?
Yeah, I think we can. You can definitely send them in. I think we had a specific slide on that. Testing services. Ken reported that you can do EQE. Right now, our lab doesn't have the capability to do IQE measurements. It just does EQE. But also most of the devices that we see in our PV lab are mostly just the chemistry. They don't have glass encapsulation on them or any protective structures. They're looking at just the the PN junction there. And we test world records that go on the NREL website on an annual basis there. So it's quite common for people to send sample cells to get an EQE in our lab. And EQE is important for determining the spectral mismatch, which we'll go into more detail in the next slide set on how that's used to compute the proper efficiency and get the correct IV curve.
Great, thank you so much. And I think we have time for maybe a couple more questions. So let's see. This next person asked, are you able to measure the IQE, EQE for high power source or power over fiber applications?
So I think that this, I think this is coming from something that's not necessarily related to PV measurement. I think they're asking about at least I believe so. I'm not sure, Dave. Ken, have you heard of any applications like this?
I'm wondering if the question is related to coupling the monochromatic light into a fiber and then moving that fiber to a different location or onto a large module where you could then use that output. I'm not sure if that's.
If that's the case, if your light source is a fiber, there's no reason that you can't have that as your IQE or EQE source. And EQ and IQE is usually measured at a point. It's not usually a broad whole device measurement. And then you just measure EQE at multiple locations on the cell. Hopefully that answered the question. Thanks, Dave.
Thank you so much. Let's see. All right, this final question we have here. What is the largest cell size that MKS PV Lab can measure for EQE or IQE tests?
Okay, and that was specific for the PV Lab. The PV Lab has some older equipment. But technically, if the edge of the cell is within about 5 inches of whatever carrier it's in, or even any portion of the cell material, we can measure an EQE of that device. We are limited with some of our other broadband light sources in the PV Lab for the full set, such as an IV efficiency and fill factor, to I believe it's 6-inch devices or 15 centimeter.
All right, great. Thank you so much. And everyone, that's all the time we have for questions now. But if we did not get to yours, please look out for a reply later. If you do think of another question, you're welcome to send an email. Our email is webinar@photonics.com. That's webinar@photonics.com. And just one final note, this whole session was recorded. It will be available on the Photonics Media website shortly, and you will receive a link to that recording by email. So finally, I'd like to thank Ken, Dave, and Todd, and thank everyone here for participating today. This webinar, it was presented by MKS Newport and hosted by us at Photonics Media. So thank you everybody so much and have a nice day.
Thank you, everyone.
Yeah, thanks.
Thank you, Donna. Thank you, everybody.